My name is Sam Anderson, and I'm a PhD candidate at the University of British Columbia. And today I'll be talking about how I use glaciers to interpret the decision-making of deep learning hydrological models. I'll start by outlining recent successes of deep machine learning in hydrology, where in 2018, a deep learning model was found to outperform a standard process-based hydrological model at over 200 basins in the United States. Shortly after, this approach was expanded to over 500 basins and was found to outperform two standard hydrological models for prediction tasks at ungauged basins. Earlier this year, the deep learning modeling approach was found to outperform 12 process-based hydrological models across the Great Lakes region in a robust model intercomparison study. The authors noted that even for the most challenging spatiotemporal validation, the machine learning model outperforms any other physically based model. While different types of deep machine learning models exist, many have been found to have this excellent performance. And so we should ask ourselves, why are these deep machine learning models so exceptionally accurate? What is it that they're learning? In short, we need to interpret the decision-making of deep machine learning models. However, along with these recent successes, there has been tension within the hydrology community, in part because of the perception that deep learning models are these black boxes. Interpreting and understanding deep machine learning model decision-making can turn this tension into a feedback loop, where known physical processes can be used to interpret deep learning models, and deep learning models can then be used to understand or represent physical processes in accurate and computationally efficient ways. I think that there are unique opportunities for Canadian hydrologists to advance deep learning model interpretability because there are unique cold region processes to study, an example of which is glacier runoff, which I will emphasize today. In this talk, I'll do three things. First, I'll briefly discuss the concepts of both glacier runoff and deep learning in hydrology. Then I'll show how we find representations of glacier runoff within deep learning models. And finally, I'll zoom out to give the broader meaning and significance of this study. The overall goal here is to find how glacier runoff is represented within a deep learning model. We'll start now by getting into glacier runoff and deep learning. Glacier runoff is important to accurately capture, since glacier-fed rivers are used for municipal water supplies, for irrigation, for hydropower. But it's not easy to model using a physical approach at regional scales, in part due to data limitations and uncertainties about processes such as turbulent heat fluxes, motivating the use of deep learning instead. To start, let's consider conceptually how glaciers alter streamflow. So consider a glacier in winter. Temperatures are cold, and so there's no glacier melt. As temperatures rise, the snowpack melts away, but the glacier ice may remain largely covered by snow, and so glacier melt remains low. Then, as the snowpack melts away and exposes large areas of the glacier, glacier runoff increases. Then again, temperatures cool below freezing, once again inhibiting glacier runoff. Two key features here are that during the early warm season, temperatures can be above zero, but glacier melt remains near zero. In other words, glacier melt is not initially linked to warm temperatures. Then, later in the warm season, glacier melt is exposed and linked to temperature fluctuations. Now, let's consider deep learning. Shown is an example of a model that uses time series of temperature and precipitation to predict streamflow. We can write this on the right, where Q is streamflow, F is the deep learning model, T and P are temperature and precipitation, and theta is all of the model parameters. For today, you can think of F as being a nonlinear regression, theta as being the regression parameters, and when we say learning, we just mean tuning values of theta to get a simulated Q that closely matches the observed Q. We use a deep learning model developed for Alberta and British Columbia that has very good performance and was published earlier this year. As input to the model, we take the past year of daily fields of maximum temperature, minimum temperature, and precipitation. As output to the model, we use the next day of streamflow at 226 stream gauge stations. Of these basins, 87 are partially glaciarized. Then the deep learning model itself has two different components. First is what's called a CNN, or convolutional neural network, and secondly, a component called an LSTM, or long short-term memory network. The CNN contains the spatial learning of the model. You can think of it as nonlinear regression through space. Then on the other hand, the LSTM contains the temporal learning of the model. You can think of it as nonlinear regression through time. Since we know where glaciers are in space, we'll investigate this LSTM component to see how and if the model has learned to represent glaciers through time. But remember, the model only knows temperature, precipitation, and stream flow. It has no information about glacier coverage, so it has to automatically learn glacier runoff from this limited data alone. With these ideas in mind, we'll now go about finding and interpreting the representations of glacier runoff within the model. To begin, we can consider the building blocks of both process-based and deep learning models. From a physical approach, we might build a model from a water balance, where we prescribe or calculate components such as precipitation, evapotranspiration, and storage. Then, streamflow can be calculated as a combination of these quantities. We could also write this equation in summation notation, where C contains the 3 prescribed states and A contains a scaling factor. Now, let's compare these ideas with the deep learning approach, which is actually quite similar. Instead of the prescribed hydrological states, there are states within the LSTM model that are learned. So these are time series components of streamflow whose form is determined by the data alone. Streamflow then is calculated as a combination of these states. The key difference between the two approaches is that here, both the scalings A and the states C are learned from the data to best fit Q, rather than having any prescribed form or sign, as was the physical case. Next, we assume that there is such a thing as a glacier runoff state, CG. Since we know basin glacier coverage, we can say that in basins that are more dominated by glacier melt, that streamflow should more closely scale with CG. There should be a stronger glacier melt component in highly glaciated basins. In other words, basins with greater glacier coverage should have streamflow that is more closely linked to this glacier runoff state. What we do then is find the states that are simultaneously very important to glaciated basins and not very important to non-glaciated basins. I'll now show the results of this process. We find that there are many such states. Out of the 800 total states across the ensemble of models, we find 56 that are strongly linked to basins with high glacier coverage. Shown here are all 56, as well as the average in black. Now we can investigate the behavior of this average pattern a bit more closely. Recall that streamflow is a combination of these states, and so an increase in the glacier state value causes an increase in streamflow in glaciarized basins, but not in non-glaciarized basins. What we can do is compare this glacier state pattern with what we suspect drives streamflow in glaciarized basins in summer. So that might be positive temperatures. And positive temperatures look like this. If we consider the seasonal cycle of both of these signals, as shown here, we can see that in early spring, temperatures rise, but the LSTM states do not initially respond. Then, through summer and into fall, they are apparently more linked, and the LSTM state decreases when temperature decreases. Considering the daily fluctuations, we can see here the daily fluctuations of LSTM states, and here are daily fluctuations of positive temperatures. Using cross correlations, we find that there is a 2-day lag between the two, where temperatures lead the LSTM state. Correcting for this, we can notice that there is a temporal structure to the correlation between these two signals. And by that I mean, there is a period, especially in summer and into fall, where the daily fluctuations are more highly linked. Using a rolling 60-day window, we can quantify how the correlation between these two signals changes through the year, as shown here. From mid-June through September, the correlation is highest, nearing about 0.8, approximately double what it is through much of the rest of the year. Let's think about what all this means. Daily fluctuations in temperature are correlated with lagged fluctuations in LSTM state, and then LSTM states are linked to modeled streamflow. So in summer and early fall, when the correlation is high, an increase in temperature from one day to the next causes an increase in streamflow 2 days later. And this feature is only present in glaciarized basins in summer and into fall. Essentially, the model has learned that there are these temperature-controlled streamflow sources that vary on both seasonal and daily timescales. Seasonally, temperatures rise in spring, but initially the state does not respond. Then, through summer and into fall, they become apparently more linked, where the LSTM state decreases when temperatures decrease. Daily, these LSTM states act like a switch, mapping lag temperature fluctuations to streamflow only in summer and fall and only in glaciarized basins. Ultimately, recall that these are two of the key conceptual features in glaciarized basins as outlined earlier. And also recall that the model didn't have any information about glacier coverage. This was learned automatically from temperature, precipitation, and streamflow. Now, I'll conclude to give some of the broader meaning and significance of this study. We show that the model learns to represent glaciers as a temperature-controlled streamflow source that activates in summer only in glaciarized basins. This is an encouraging finding that's consistent with a conceptual understanding of glacier runoff in these basins. This allows us to build trust in the model's predictions related to glacier runoff in the region. Furthermore, it's encouraging because it suggests that physical processes may both be learned and also interpreted by us as researchers and users of the model. While we considered one model structure and one process, there is opportunity here to think creatively about other processes and models to investigate and to develop other methods to do so. So thank you very much. For those who are interested, code is available on my GitHub here to reproduce the figures in this talk, and the associated papers are also listed on this slide. You can email me directly or follow me on Twitter for future updates or any questions you might have. Thank you.